You're going to be in this.
Okay, everybody, let's get started. Okay, listen up. So you're writing about all 4 of these different projects, not just one. Pay attention to them all. Your first paragraph should include all 4, and then your second paragraph, talk about which one you like the most, or which one you want to focus on, or what you'd like to do when you're a senior, maybe, something like that. Okay, so without further ado, the Waste Solutions crew, go ahead.
So we are Waste Solutions. I'm John, this is Derek, and this is Christina. And Raphael is not here today, so you will only be seeing us 3.
Okay, so we're looking to start a composting facility on campus. That's the idea behind our project. And one main reason for the idea is sustainability. So sustainability is the idea that everything we need for survival depends directly or indirectly on our natural environment. And the 3 pillars of sustainability are the environment, the economy, and society. And this has also been an important topic for Pope Francis. And so as a Franciscan institution, this is something that we can do too. So starting with the problem description. Okay, so starting with the problem description, we're looking at food waste at Torbian. And at Torbian there are 2 waste streams, pre-consumer and post-consumer. So pre-consumer waste is food that was used to make the food that didn't actually, like any food scraps that didn't get cooked. And then the post-consumer waste is any food that was cooked but wasn't eaten, or food that students left on their plates. So in total, the pre-consumer waste there is about 330 pounds a day at Torbian, and the post-consumer waste there is just below 500 pounds. So in total, every day, there is about 800 pounds of food waste that is wasted at Torbian. And in a semester, that's about 60,000. So where does that food waste go? About half of it goes to the landfill, and that is the majority of the pre-consumer waste goes into the landfill. A little bit of the pre-consumer waste goes into a small compost pile that was started last year. It's like right outside of the entrance to Torbian. But the other half goes to the wastewater treatment plant, and so that is any food that wasn't eaten, gets put into a disposal chute, cut up, and then it goes to the wastewater treatment plant. And then energy has to be expended in order to take it back out of the water. So looking for potential solutions to the food waste, there's a food recovery hierarchy that's published by the EPA. And at the top of the pyramid, that's the most environmentally friendly, the most sustainable options. So it starts with source reduction. So on the left are things that Torbian and the school already does, and on the right are different options that we can add onto the management plan. So at the top, some of the food scraps that are not used go into the soups. Torbian also, one thing that should be on there is that Torbian workers take home any extra food as well that isn't eaten. Another thing is that the oil and grease that is used in the food that comes out of it, they send it to a company that uses it to make soap. Also, the small composting bin that we already talked about, and the majority of it goes to the landfill and wastewater treatment. So things that we can add to it are doing some education so that students and also Torbian doesn't make so much food that isn't eaten. Another thing is sending it to feed local animals and the composting option. So the first option that we're looking at is feeding animals around the area. So this is very cost effective. It's high up in the food hierarchy. But because of increasing inspections for different farms, it's not a very used option by farmers. And logistic-wise, the food has to be fresh in order to feed it to the animals by law. And so you might have to have a refrigeration system on your farm, and that's also expensive. Another option, which isn't higher up in the hierarchy, is sending things all the way to the landfill. This could potentially be more cost-effective than building a composting facility, but it would possibly save energy and water that would be used at the wastewater treatment plant to take the food back out of the water stream.
Onto our final option would be to compost and build a composting facility. So we have 2 different types of options. Our first option is to compost off campus, and that would require us to gather our waste and send it to a local facility. There's a local facility about 12 miles away from here, and they're thinking about implementing a food waste composting system. So that would be an option. They talked about having possible free pickup, so that would be extremely cost effective for us to send our waste to them. So the other type of composting that we would like to do would be to compost here on campus. The benefit of composting here on campus is that we would generate our own product. We would come up with our own compost that we could use to spread on the local gardens and anywhere that they have brush or gardens that you want to put compost in. It's also close to the source, so you can just take it right from Torbian and then drive it with a truck or something and just dump it off right in our local compost facility. It's also a higher hierarchy than landfill. It's just one up, but it is eventually something that's going to have to be done. You can't just go up the hierarchy the whole way, but you have to take baby steps because you're always going to have waste. So the different methods for composting. The first type is windrow composting. This is very common in large applications. They essentially have large rows, and right here you can see a windrow turner, and right here is a windrow turner. And what that does is they just go over the rows and they turn the compost to give aeration. Another method is in-vessel composting style, and this is extremely cost effective because you don't use large machinery like for windrow composting. This is very beneficial for us because up behind Ave Hall, where they are already mulching their yard waste, they have a lot of these already up there, so if we would coordinate with them, this could be a possibility. Another more advanced, I guess, method would be a static aerated pile. And this uses the use of blowers and hoses or tubing that would be inside the pile, and it would pump air into the pile so you wouldn't have to mechanically turn it. Then another method is vermicomposting. Now vermicomposting is using worms in conjunction with the microbes that are already in the compost to break down the waste. Vermicomposting is good because the worms can break down waste a lot quicker, but it's got some bad cons to it too, because the worms can be very picky. Microbes aren't as picky, but the worms are. So dairy products, meat products, stuff like that, they can kill off the worms, and then you have a nasty smelling bin, which we'll talk about later. So in order for composting to work, you need a moisture content of 40 to 60%. You need to have sufficient oxygen and get aeration. So that's going to be one of our main things to overcome with picking our type of facility. You want your temperature not to exceed 55 to 60 degrees C, because it could start killing some of the microbes. pH, you want to have a pH of around neutral. This is mainly picky with vermicomposting. Worms are very susceptible to pH changes. And of course, the most important is to have a good carbon to nitrogen ratio of 25 to 30 to 1. So our carbon sources would be like our yard waste or our office paper, while the nitrogen would be coming from food. So like I said, nitrogen-rich food waste has a carbon to nitrogen ratio of 14 to 16 to 1. So that means there's 14 to 16 parts of carbon for every part of nitrogen. Now, as you see, the carbon materials like yard waste and paper are a lot higher than our nitrogen-rich food waste. So doing about like a 50-50 between those, we would get to about 25 to 30 to 1. So now our current yard waste inventory that we have here on campus. You can see in this table that we produce a lot of leaf litter and branches. So they're currently being composted or mulched behind the Ave residence hall. It's turned a couple times a year. It produces 86 to 113 cubic yards per year of yard waste. So this yard waste can be used with our food waste, but we will still need an additional source of yard waste, or a carbon source, to be able to offset our food waste that we're producing. So we will need approximately 300 cubic yards per year of yard waste in order to treat essentially our food waste. And currently we only have 150 cubic yards. Now we can supplement our extra 150 cubic yards with paper that we get on campus.
So in order to test what mixtures were the best, we did a quick experiment. We did a bunch of different mixtures and we mixed them up in bins and we did triplicates of each in order to picture the data together. That's just a chart of what mixtures we did. To save time, I'm not going to go over each one of them and see what we did on the chart. This is just a picture of the food waste at the bottom of the bin. We made sure it was really minced up and had a small particle size, so it would break down a lot more quickly and easily. This is the food waste mixed with just some shredded paper. This is some data that we collected. As you can see, what was doing the best in the beginning was both of the mixtures together. Unfortunately, because of the small size of the bin and how it was set up, they didn't do too well over time as we had hoped. But based off the initial data that we obtained, we can see that mixture of yard waste and shredded paper with food seemed to do the best. So the next steps that we would take after the experiment and after what we did last semester is we need to determine a facility layout and what operational requirements we need. We need to do education management. We need to do a sustainability assessment and economic assessment, and then determine how we're going to transport the food waste and collect it, as well as the feed carbon materials. And then we just like to give a special thanks to the Torbian staff, physical plant, intermunicipal relations committee, and measurements one class who helped us mix up everything we expected there.
Coming up and get ready while they're transitioning out. We're going to do questions afterwards, so please write down if you have a question and which group it was for. I have one more announcement while we're switching out people. I know that there is a microbiology lab after this at 3 o'clock. Just because people are standing up to leave exactly at 3 o'clock doesn't mean everyone can leave. If we still have questions, stay here for a couple minutes, okay? So only those who have class can leave right away.
So, for all of you who don't know us, I'm Amber.
I'm Jordan. I'm Angela.
Ryan.
Louder.
Okay, and we're the effluent engineers. Our senior capstone project was on redesigning the wastewater treatment plant on campus. Okay, so some little background on wastewater treatment plants in general. Our wastewater treatment plant on campus is an activated sludge plant. What an activated sludge plant does is it uses microbes to break down raw sewage. And this technology wasn't really popular until the 50s, but the first one was invented in the early 1930s. Our plant was built in 1966, so it was pretty early on. And we get a small flow of 84,000 gallons per day.
So this is the plant that we have here at school. If you go around and you see a lot of plants, this is very representative. It represents what most of the plants would look like around in this area. So the first step, the influent, so that's the water coming straight from your toilets or shower or toilet, like was said before in the last one. It goes to the common neuter, and And what the comminutor is, like a giant garbage disposal, and it's gonna grind all the particles and stuff into really small pieces, so that it has a greater surface area for when it gets to the next step, which is the activated sludge aeration basins. What we have here at school is a 24-hour retention time, which means the time that it takes for the influent to get from this spot to the end, it's going to take 24 hours. This is truly a biological process. The microbes that break down all the organic material that's coming in is happening in this area. You pump air into the aeration tanks to have a high concentration of microbial life. So that's what they live off of. So then the next step, it goes to a clarifiers or settling tanks. That just uses gravity to get the particles from floating down to the bottom, where then it forms sludge and then that's scooped up. The next step will go to a chlorine contact tank. There's 2 tanks. Normally there's only 1 in use, and we'll switch them if like one needs maintenance or whatever. As you can tell by the name, chlorine contact tank, we're putting chlorine, well, here they use chlorine gas to go into the water, and that kills any pathogens or any extra microbial life that's trying to, not trying to, but in the water going to leave the plant. The next step is dechlorination. We here use sodium bisulfate, so we mix that into the water to get